Hi, this is Mrs. Ward, and today we're going to go over section 2.5, complex numbers and their roots. The objective of today's lesson is to define and use imaginary and complex numbers, solve quadratic equations with complex roots. The vocabulary for this section is imaginary unit, imaginary number, complex number, real part, imaginary part, and complex conjugate. So when we begin, we're going to start with a quadratic equation, which we're familiar with. And we're going to start with the equation of x squared plus 1 is equal to f of x. If it asked me to find the zeros of this equation, we would set it equal to 0. And we saw we would get x is equal to plus or minus -1. When you try and take the square root of a negative number, we've always said that it has no real solutions. And that is true. The equation has no real solutions. Because when I look at the graph, here's my parabola. It never crosses the x-axis, so I have no x-intercepts, therefore I have no real solutions. But what we're going to do today is we are going to talk about the imaginary unit. And the reason why the imaginary unit was invented was so that we could solve the square roots of negative numbers. The imaginary unit is the letter I, which is usually italicized, and the imaginary unit is going to be defined as the square root of -1. So I can rewrite the square root of any negative number as the imaginary unit times something else. So let's see what that looks like. So if I have the square root of -1, I'm just going to call that I. If I had the square root of -2, I'm going to separate -2 as the square root of -1 here times the square root of 2. The square root of -1 is defined as I, and then I'm going to have the square root of 2. If I had the square root of -4, I'm going to separate that as the square root of -1 times the square root of 4. The square root of -1 is this I, just positive I, sorry, and the square root of 4 is 2. And lastly, if I take the square root of -1 squared, the square root and this raising it to the second power are inverses of each other, so they kind of undo each other. So this would be, the square root of -1 would be I, so this would be I squared. And so then I'm going to define that as -1. So to recap, if I take the square root of any negative number, I'm going to make it I times the square root of that number positive. Take the square root of a negative positive, take the square root of a negative perfect square, it's just going to be b times I. And if I take the square root of a -b squared, it's just going to be -b. So let's see how that works with real numbers. So the first example I have here is I have 5 times the square root of a -121. So I'm going to write this again as 5 times, I'm going to separate the square root of -121 as the square root of -1 times the square root of 121. 5 still stays out in front. It's still being multiplied, so I'm going to multiply it. Square root of -1, I'm defining as the letter I, my imaginary unit. And the square root of 121 is 11. When I go to multiply, I'm going to multiply my constant. So I'm going to take that 5 times 11 and get 55 times I, which I'm going to write as 55I. So 5 times the square root of -121 is equal to 55I. Let's do another one that isn't a perfect square so we can see how that looks. So the next one I have is I have the opposite of the square root of a -96. Now remember, I can't distribute this negative side inside the square root, so I'm going to leave this outside. I'm going to have a negative or a -1 times, and then I'm going to separate that as the square root of -1 times the square root of 96. Here's the negative sign again. Square root of -1 is going to be defined as I. 96, I'm going to look for the largest perfect square, which is going to be 16. So I'm going to separate that as 16 times 6. The square root of 16 is 4, so this will be negative times I times 4 times the square root of 6. When I write this, I'm going to take my real number and I'm going to put it out front of the I. So I'm going to write -4I times the square root of 6. That's one way to do it. If I look at the square root of 96, I'm just going to go off here to the side. Square root of 96. If I don't like doing it this way where I find the largest perfect square, you can do the factorization tree. And I'm going to factor 96. Let's say I factor it as 8 times 12. 8 I can factor as 2 times 4. 4 I can factor as 2 times 2. So those are all my prime numbers so far. Factoring 12, 3 times 4. 4, 2 times 2. Remember, to come out of the radical sign, you have to have a pair. So here's a pair of 2's. Those are going to be outside the radical sign. Here's another pair of 2's outside the radical sign. This 2 and this 3 are still part of the prime factorization of 96, but they don't have a pair, so they can't come out. So they have to stay underneath the radical sign. So that's going to be 2 times 3. When I multiply, 2 times 2 is 4. Radical sign 2 times 3 is 6. 4 times the square root of 6, which is the same thing I got here. So either way you want to break up that radical is up to you. Now we're going to solve quadratic equations with imaginary solutions. So we're going to start with a simple one where I do not have a middle term. I just have x squared is equal to negative 144. Notice that the x squared is on one side by itself with a coefficient of 1. So what I'm going to do is to solve this is I am going to take the square root of both sides. So I'm going to say square root, square root. Square root of x squared is x. When I take the square root and I'm looking for a solution, I'm going to write plus or minus because it's going to either be positive or negative. And then I'm going to separate the square root of negative 144 as the square root of negative 1 times the square root of 144. X is equal to plus or minus square root of negative 1 is defined as I. Square root of 144, that is a perfect square, and that will be 12. When I multiply, I'm going to get x is equal to plus or minus 12i. So my two solutions are going to be positive 12i and a negative 12i. And you can write it like this, or I can separate it. That's up to you. So let's do one that's a little bit more challenging. Here I have 5x squared plus 90 is equal to 0. Still, I do not have a middle term. I don't have just an x term. So in order to solve this, the first thing I have to do is I have to isolate this x squared on one side by itself. First step to doing that is to subtract 90 from both sides. And then I'm going to have 5x squared is equal to negative 90. I want this x squared on one side by itself, so I have to divide both sides by the 5, so it has a coefficient of 1. When I do that, I'm going to have x squared is equal to negative 18. To solve this, I'm going to take the square root of both sides, square root, square root. So when I do that, I am going to say x is equal to plus or minus, because I took the square root and I'm solving an equation, square root of negative 1 times the square root of 18, separating that negative out. I'm going to have x is equal to plus or minus square root of negative 1, again is defined as I, times, and I'm going to separate 18 as the square root of 9 times the square root of 2. Then I'm going to take the square root of 9, which is 3, so I'm going to have I times 3 times the square root of 2. And then to clean this up a little bit, I'm going to say x is equal to plus or minus 3i times the square root of 2. So my answers are 3i plus 2 and negative 3i plus, oh, that's square root of 2. Got my square root sign. There you go. So those are my two solutions. Again, I can leave it like this down here, or I can separate into the two separate ones. That is your choice. Now, a complex number is a number that can be written in the form of a plus bi, where a and b are real numbers and I is still defined as the square root of negative 1. The set of real numbers is a subset of the complex numbers. So here's the real numbers that we've been working with pretty much our entire lives. We just introduced the imaginary numbers, which is when I take the square root of a negative number and I introduce the I, the imaginary unit. A complex number has a real part and an imaginary part, and I'm adding those together. So this complex number 3 plus 7i, the real part is the a, so the 3. So here I'm going to go down here and show you. We had 3 plus 7i. This 3 is my real part, and that would be, so my a in this case would be equal to 3. 7i would be my imaginary part, and in this case my b would be equal to 7. So this is my real part, this is my imaginary part. When I put them together, I form a complex number. Now you can have a complex number. Real numbers are the numbers that we've had so far. If I have something like 4 and just 4, 4 is a complex number where b happens to be 0. So I would have 4 plus 0i, and we would just write that as 4. So that is a real number. If we have something like 0 plus 6i, here my real part is 0, and I just have the imaginary part. That's called a pure imaginary number. And then anything that has both a real part and an imaginary part, those are your complex numbers, your regular complex numbers. So in order for two complex numbers to be equal, the real parts have to be equal to each other, and the imaginary parts have to be equal to each other. So I'm going to slide this down here for a second and show you. So if I give you, let's say, 3 plus 4i, and I ask you to write a complex number that's equal to 3 plus 4i, your a would still have to be 3. Your b would still have to be that positive 4. So this is how I have one complex number is equal to another complex number. Well, that looks fairly simple. Now let's make it where I have to solve for a variable in order to set two complex numbers equal to each other. So in this case, I have 4x plus 10i is equal to 2 minus 4yi, and I want it to be true. In other words, I want these two complex numbers to be equal to each other. So if I'm looking at my real part, that's going to be this 4x. The real part on the right side is this 2. The imaginary part would be this 10. The part that has the I would be 10i. And the imaginary part over here, and here, let me make that sure that I know that that's a positive 10i. And over here, it would be negative 4y times the part that's connected to that I. So see how they both have I? Well, I'll do that later. So let's solve this. So in order to solve this, I would take my real parts, which are highlighted in yellow, and I would set those equal to each other. So I'm going to say 4x is equal to 2. I'm solving for x, so I'm going to divide both sides by 4. And in this case, x would have to be equal to 1/2. When I'm solving for the next one, when I'm solving for the b, to make the imaginary part true, I'm going to have this 10 and this negative 4y, and that's a positive 10, just to make sure. That's a negative 4y. I don't need the i's because they're attached to both, and that's what's telling me it's the b. It's the part that's with the imaginary unit. So I'm going to say 10 is equal to negative 4y. Solving for y, I divide both sides by negative 4. And I'm going to get y is equal to a negative 5/2, or you can have negative 2.5. Whoopsie, went a little bit too far. So negative 2.5. So in order to make these two complex numbers true, equal to each other, the x would have to equal 1/2, the y would have to equal negative 5/2 or negative 2.5. And that would make the left side and the right side equal to each other. Now we're going to find complex zeros of a quadratic function. And it's asking us to use completing the square technique. So now I have f of x is equal to x squared plus 10x plus 26. Just to clarify, when I'm finding the zeros, that means I'm going to set this equation equal to 0. So I'm going to say 0 is equal to x squared plus 10x plus 26. When I go to complete the square, I'm going to want to take anything with a variable and leave that on one side. Anything that doesn't have a variable, I'm going to want to take over to the other side. So in this, to get the 26 on the other side, I'm going to have to subtract 26 from both sides. So I'm going to have negative 26 is equal to x squared plus 10x. To complete the square, what I'm trying to do is I'm trying to make it a perfect, like x plus some number squared. That's what I'm trying to do when I complete the square. So I have to figure out what number I'm going to put here. In order to do that, I have this method where I take the middle term, which in this case is 10x. I look at the coefficient, which is 10. I take 10 and I divide it by 2. That 10 comes from here. 10 divided by 2, well, 10 divided by 2 is 5. 5 squared is 25. So I'm going to have to add 25 to this side. And if I add 25 to the right side, I'm going to have to add 25 to the left side. The reason why I did that is now I can rewrite this x squared plus 10x plus 25 as x plus 5 squared. And if I were to FOIL that out, I would end up with this 10x squared, or I would end up with this x squared plus 10x plus 25. All these numbers, the 25 is here. This 5 comes from here. It's to the half of the middle term. And the sign that I put inside the parenthesis is the same sign that's in between the first and second term. It's always the same sign. When I add this negative 26 plus 25 here, when I add these two, I'm going to get negative 1. Now I have something that's squared on one side by itself, even because the whole parenthesis is squared. So in order to solve this, I'm going to take the square root of negative 1, take the square root of x plus 5, that quantity squared. The square root of negative 1, remember that's the imaginary unit I. And then here I'm going to, that's a mistake, something else. I'm going to take the square root of x squared plus 5. I'm sorry, I'm going to take the square root of the quantity of x plus 5 squared, which will just be plus or minus, because I'm taking the square root and I'm solving, of x plus, oh no, I did that wrong. This is x plus 5, I agree with me, but the plus and minus sign should actually go here when I took the square root, because this is the side that I'm solving for. So I have plus or minus I is equal to x plus 5. So I have two separate solutions, two separate equations that I have to solve for x. One is going to be this positive I is equal to x plus 5. And the other one is going to be that negative I is equal to x plus 5. To solve both equations, I'm going to subtract 5 from both sides. Subtract 5, subtract 5. So again, keeping in the form that we just learned from the complex numbers, that a plus bi, where my real part is going to go first, I'm going to have negative 5. That's going to come first. Plus I is equal to x. Over here, I'm subtracting 5 from both sides. Keeping the real part in front, I'm going to have negative 5 minus I is equal to x. And those are my two solutions. Negative 5 plus I and negative 5 minus I are my two solutions. Let's try another one. So here I'm going to find all the zeros again. So again, it's asking me to find the zeros of the function. Zeros means that I set the equation equal to 0. It's going to be 0 is equal to x squared plus 4x plus 12. The directions are telling me to use the complete the square technique. So the first thing I'm going to want to do is leave everything with the variables on one side. This 12 is going to go over to the other side. So I'm going to subtract 12 from both sides. And when I do that, I get negative 12 is equal to x squared plus 4x. And now I know I'm going to add some number, and I'm going to try and figure out what number that is. Sometimes I like to sort of do a step ahead while I'm working. And I like to say, well, I know I'm going to make this x. This is a plus sign, so I'm going to copy down a plus sign. I've got to figure out what number I'm going to put here, squared. I'm going to look at my middle term. My middle term is this 4x. So I'm going to over to the side. I'm going to take 4 and I'm going to divide that by 2, because you always take half of the middle term. Then I'm going to square that. 4 divided by 2 is 2. The number that I have here is the number that goes here. So I'm going to write this as x plus 2 squared. And then when I take 2 and I square it, I get 4. That number goes here. Here, I just added 4 to the right side of the equation. I can't just randomly add a number without adjusting for it. So if I add 4 to the right side, I have to add 4 to the left side. And so the negative 12 plus 4, that'll be negative 8. So now I have negative 8 is equal to x plus 2 squared. So I am going to take the square root of both sides. So square root, When I do that, I'm going to think of this as the square root of -1 times the square root of 8 is equal to, oh, and there's a plus or minus out in here, is equal to x plus 2. Here, this will be 8, I'm going to think of as the square root of 4 times the square root of 2. Oopsie, sorry, that's kind of messy. And so I'm going to have plus or minus, and then I times 2 times the square root of 2 is equal to x plus 2. Making that a little bit, cleaning it up a little bit, I'm going to move the 2 out in here. So I'm going to plus or minus 2I times the square root of 2 is equal to x plus 2. So now I'm going to separate it. So now I'm going to solve. In order to solve for x, I'm going to have to subtract 2 from both sides. And I feel like before I should do that, I should have 2I times the square root of 2 is equal to x plus 2. And I should have negative 2I times the square root of 2 is equal to x plus 2. Now I subtract 2, keeping my real part in front. I'm going to have negative 2 plus 2I times the square root of 2 is equal to x. And over here, when I subtract 2, I'm going to have negative 2, let's see, negative 2 minus 2I times the square root of 2 is equal to x. And you should notice that these answers look pretty similar. I mean, both of them have a real part of negative 2. We're going to highlight some things here. Both of them have a real part of negative 2, and then the imaginary part is this 2I times the square root of 2, and this will be 2I times the square root of 2. The only thing that's different between these two is one has a plus sign and one has a minus sign. And that's the next thing we're going to talk about. We're going to talk about this. When I find the solutions of a quadratic equation, they're going to come in these pairs, which we call complex conjugate pairs. And the real parts are going to be equal, the imaginary parts are going to be equal, but they're going to be opposite. So one's going to have a plus sign, one's going to have a minus sign. If a quadratic equation with real coefficients has non-real roots, those roots must come in those conjugate pairs. So, and this hint says that if you're given one complex root, you can always find the other by finding its conjugate. So we're going to practice finding the conjugates. So the first one's pretty straightforward. I have 8 plus 5I. Notice it is written in what I call standard form. By standard form, I mean the real part is first, the imaginary part is second, and it has to be in that order to find the complex conjugate. The real part has to come first, the imaginary part has to come second. So when I go to find the conjugate, I'm going to keep my real part as 8, and then change this plus sign to a minus sign, and 5I. These two are complex conjugates of each other. Then when I look at B, I have 6I, which is a pure imaginary number. I can think of that as 0 plus 6I, where 0 is my real part, 6I is my imaginary part. To find the complex conjugate, I would leave the real part as 0, and then take the opposite of plus 6, which would be minus 6. So 0 minus 6I would be my complex conjugate, or I could just write negative 6I. Either one would be fine. When I'm looking at the next one, they're trying to trick you, and don't fall for it. See how they have 2I minus 7? That is not written in standard form. To write it in standard form, you have to have the real part first, the imaginary part second. So in this example, my real part is this negative 7. My imaginary part is this 2I. So when I go to write this, before I can find the complex conjugate, so I do not make a mistake, I am going to write it in standard form. So I'm going to write negative 7 plus 2I. These two are equal. I've just rewritten it in standard form. To find the conjugate, I'm going to leave the real part as negative 7, take the opposite of 2, which will be minus 2I. And this is the conjugate. Do not make that mistake where you forget to put it in standard form first. You must put it in standard form first. We're going to do another one. Here, they're trying to trick you, but you're not going to fall for it. Your real part is this plus 6. Your imaginary part is this negative 4I. So first thing you're going to do before you even think about finding the conjugate is you're going to write it in standard form. So I'm going to write 6 minus 4i. Again, these two are equal. I've just rewritten it in standard form. To find this conjugate, I leave the 6 alone. Take the opposite of negative 4, which is a positive 4i, and this is the conjugate. Okay, just making sure that we did everything we said we were going to do. We defined and used imaginary and complex numbers, and we solved quadratic equations with complex roots. Just to give you a refresher course, or real quick down, the imaginary unit, remember that's the square root of negative 1, and that is I. That's my imaginary unit. An imaginary number is something like 6i, or it could be like the square root of negative 7. Those are imaginary numbers when you're trying to take the square root of a negative number. A complex number means that I have a real part, let's say 4, plus an imaginary part, which is 3i. Complex number has both a real and imaginary part. Sometimes one of these can be equal to 0, but this is the standard form of a complex number. Again, the 4 in this case would be the real part. The 3i would be the imaginary part. A complex conjugate is once you have this written in standard form, so we're going back to my 4 plus 3i. The complex conjugate is where you leave the real part alone and you take the opposite of the imaginary part. So this would be the complex conjugate of 4 plus 3i. I hope this answers all of your questions. If you have more, come see us in class and have a great day.